Good morning. I'm Sophie Rovner. Welcome to this news briefing from the 254th National Meeting and Exposition of the American Chemical Society here in Washington, D.C. We're joined today by Dr. Eric Masson and via Skype, Dr. Saw-Wai Hla, both from Ohio University. They led one of 6 teams that participated in the world's first nano race this spring, and we'll talk about what they learned from entering their nano-sized monster truck. Dr. Masson.
Thank you, Sophie, for the introduction. And first, I would like to thank ACS for inviting us to give this press conference. So today we will introduce you to our Ohio University Bobcat Nano wagon that participated in the first Nano Car Race in Toulouse in April. The Nano Car Race was organized by Christian Joachim from the CNRS in Toulouse. And the main goal of this, there were 2 goals associated with this race. The first one was to promote science, and in particular nanoscience, to the general public. And the second goal was to exploit the capabilities of this beautiful instrument, this beautiful scanning tunneling microscope that has 4 tips. It's a unique instrument, so that was the second goal. So the way the race worked is that there were 6 teams, and each team had to be able to deposit a molecule that would be the car on the surface, and then to control the car with the tip of an STM microscope. So as I said before, there was this general goal of promoting science, and then each team had their own goals. And ours was to deposit a supramolecular car, and I'm going to get back to this in a minute. Deposit a supramolecular car on the surface and be able to control it. So what do I mean by a supramolecular car? It's a car that is made of several pieces that interact non-covalently. So there are no bonds between the different parts of the car. And our car has 5 parts. So if I can move to the slides. So what we did, what my group did, my graduate students did, was to design the car and to synthesize it. And then Professor Hla will take it from here and talk about the manipulation by STM, which is a real challenge. So first about the preparation and the synthesis of the car, we synthesized an H-shaped chassis that you can see on the slide. There is a drive shaft right in the middle, and there are rear and front axles. And the car is positively charged. If you look at it closely, you will see that there are 6 positive charges on the frame, right? And then what we did is to, after doing the synthesis, which took us quite a while, was to suspend this chassis in water. It's not water soluble, so it's a white solid suspended in water. And then we add 4 equivalents of cucurbituril. So cucurbituril is the wheels. My group has been working on cucurbituril chemistry for about 9 years. And the cucurbituril is a pumpkin-shaped molecule that has a hole in it. So it's a hollow macrocycle. And well, if you look at it, it really looks like a wheel. So we thought that it would make perfect wheel for our nanocar. So we've got our chassis in water, and then we add 4 equivalents of the wheel, and then the car dissolves. So adding the wheels dissolves the frame. Surprisingly, you need all 4 wheels to make it water soluble. You can see at the bottom of the slide some Nmr Spectra for our cars. We designed 2 of them with a short drive shaft and a longer drive shaft. The Nmr spectrum looks pristine because the molecule is so symmetrical that, of course, it looks simple. Well, then we have our nanocar in water, and then we just freeze dry it. So we remove the solvent. We're left with this white solid, like billions of nanocars, and then we transferred that sample to the group of Professor Hla, who did all the STM manipulation and who will also give more details about the race. So, Professor Hla, please.
Thank you, Eric, Professor Masson, of the powders. So our first task basically is to deposit these molecular cars on the substrate. We use a gold substrate, so we have to test several times how can we deposit intact. So we need to get those cars intact on the substrate, which is the gold crystal surface. And then the position condition, basically we heat them up in the molecular salts that we built ourselves, home built, and then the molecules fly in ultra high vacuum, which means that there is no air inside the chamber. So only the molecular cars will be go and stick to the substrate. And then we check that we got the cars or not, and by taking the scan tunneling microscope, the images, when we got those the images, then the next step, of course, we have to learn how to drive the car. So the car synthesized by Professor Masson already has this charge points. The idea is that we are going to use the electrical energy from the scanning tunneling microscope tip to drive the car. So in the slides, what you are seeing here is that in the figure, the first figure A, there are three numbers. You will see 1, 2, and 3. This is the snapshots of what's happening when we took the image. The one is actually intact car, also number 2. And those streaks that you see are actually, the cars are moving already. But this image was taken at liquid nitrogen temperature, so that kind of about 80 Kelvin, or 80 Kelvin. And a B, which is, I will say, is a great result, because we need to confirm that the wheels are intact, our thermal evaporation. So, and it turned out that the wheels are intact, and we were super happy, because if you look at the figure, you will see there are 1, 2, and 3. The 3 wheels are intact in the car, and the 4th one is broken. So we can confirm that the wheel can be intact. In this case, the car is immobile because you have one wheel is broken. So I stopped there. So that was nice. And figure C is showing that the shape of the wheel. Okay, so that's the how it looks like. That's the image. The green one is the during the manipulation when during the race, the Nano Car Race, the 4 wheels that you see the image are in action. So we'll look to the car use that electrical energy to move forward, and this is we can also control the directions either to move forward or backward by changing the polarity of the electric field that we apply to the car. Okay, thank you.
Thank you very much. Are there any questions? And if so, please state your name and affiliation before asking your question.
So it's Kath O'Driscoll from Chemistry and Industry magazine. I'd just be interested to know, how do these nano cars actually travel differently to sort of macro scale cars? And maybe you can say a little bit more about the competition, which car won and maybe why it won. Are these cars affected by sort of weight issues like macro cars would be, and friction and things like that?
Okay, so can I?
Sure.
I will just say a few words here. So first of all, I forget to mention one thing. So this was the first time that we have manipulated the cars across Atlantic. So our cars were located at the Ohio University in our lab, in the STM, and we operate from France. So we made atomic manipulation from France across Atlantic Ocean for the first time. And during the event, there was a storm crossing, including the Washington, D.C. It was the last week of April. And that produced power outage for us. And that was one of the reasons that we did not succeed to the end. Now, however, we got the third prize. Now, how that will drive the friction, that is, in my opinion, a very important question, because the friction is the key here. And all the indications are that it has a very, very low, probably even supramolecular status, supralubricity. We have not confirmed yet. We are now trying to measure how much lateral force will be needed to move or to drive the car, and at the single car. Right now, in my group is now working on that. The driving things is different from our macro scale cars, because in our macro scales, the gravity is the key. So if you think about the car, if you put it on the slope, if you put it the free gear, the car will fall and slide it down. At the nanoscale, gravity or gravitational force is not important. So the interactions between the wheels and the substrate are the key. So how they interact is the key. The unique things with my experience with manipulation of the molecules, these cars are more or less themselves, in a way, they interact very, very less. They are physically stuck on the substrate. That's why they're already mobile at the liquid nitrogen temperatures. We need to freeze it to the liquid helium temperature in order to control driving the car.
Thank you. Dr. Masson, would you like to add something to that?
Sure. So what's also important to understand is that the chassis, right, the H-shaped chassis is suspended into the wheels. So that there is some built-in suspension in there. It floats into the wheels. And also the interaction between cucurbitural, so between the wheel and the chassis, is extremely strong. Already in water, the interaction between those microcycles and selected guests are the strongest ever. So it beats natural systems. So a cucurbitural and a selected guest will have an affinity that is 200-fold or even 500-fold higher than the tightest interaction in nature. So the wheel interacts extremely tightly with the chassis. However, the wheel will roll freely. And my group is running calculations at this time. And so the wheel is well assembled into the chassis, but it really rotates with a very low barrier. So that guarantees a rolling motion that can actually promote a rolling motion on the surface. Now, as Professor Hla was saying, we don't know at this stage whether the car is sliding or whether it's rolling, but it can definitely roll because, again, there is very little friction when the wheel spins around the chassis.
I was interested too to find out about. I understand that you control them remotely and used. I guess it's sort of an electrostatic, just this repulsion force to actually move the cars. Are there other applications? I mean, how could this be applied to sort of nano devices in the future? How might these sorts of findings play out?
Okay, so of course, this is the starting point. For us, both and I consider that this is just the beginning for us, and we start from here. So if we apply the electric field, for example, if we want to, our goal is to develop a kind of a linear transport system and control linear transport system that can be operated on material surfaces. Okay, so that's the one of our key goals. So right now we can apply the electric field, and that is already an advantage. And we can change the design of the molecules, for example, to accept the light by means of the photons. Maybe we will be able to drive, and we probably will be able to easily to assemble these cars and make us ordered kind of the structures, and maybe we can move many cars at once by applying the electric field or by light. So that probably will become very applicable for the material science or maybe for industry.
Thank you. Also, how important is it to control outside environment factors? I know you mentioned the temperature control, and I think you said they were in a vacuum. How do those sorts of environmental factors affect nano devices or the nano cars?
In my opinion, Eric, you might add later. So my opinion is that this is it's good. We want to understand about the single car. That's why we try to control the environment. But actual deposition, because this is the molecules, for sure, chemist knows very well. I'm sure Eric knows very well. You can directly deposit it from the liquid phase. And that will be very cheap, and there will be all the cars will be there, for example. And it seems to me that the car is also not too interacting with others. So I do believe that's easy. If we want to control the environment, for example, for semiconductor devices, if we want to combine with these cars with the semiconductors, then we need to control the environment. We need an ultra-high vacuum, like many other semiconductor devices when you fabricate. then we can also use this car in that case. Unlike other molecules where it would disintegrate, the car is not integrating. It's not disintegrating, it's intact. Another amazing thing for us, actually I was surprised, is that although they are chemically not bonded, the wheels are chemically not bonded, but they are intact, they survive. That's amazing. And molecule, you know, the carbon-carbon bond is the strongest, as we know. But we can break the carbon-carbon bond. To take out the glue is not that easy. So that is another amazing thing scientifically as well. Eric, you might add.
Yes.
Because
So in that case, what we noticed is that during the deposition process, is that the car would break in half. So we would see hoverboards or segways on the surface. So just an axle with two wheels, but the wheels would stay on. So basically, what we did is to break a covalent bond via a reaction that we do not understand at this stage. But we broke the chassis in half, but we were not able to break the wheel, the connection between the wheel and the axle, which is really strange. And also, it's the first time that we can image a such a big supramolecular system. Again, it's five parts combined, right? And also, you were talking about the requirements to like conditions. So on the chemical side of things, we need water to assemble the wheels. So we cannot use another solvent. We cannot just use a solid chassis and just grind the wheels into the chassis. The chassis has to be suspended in water, and then the wheels have to be dissolved in water. Everything self-assembles nicely exactly where we want them to self-assemble. And then we have the car in water, but water has to be the medium of choice to assemble the car.
So yeah, the release mentions something about the non-covalent bond being stronger than the covalent
That's correct.
bond.
Yeah.
In this case, how unusual is that? I mean, is that at the first occasion that this has been found, or?
To the best of our knowledge, it's the first time that this is being observed. As I said before, the bond between the wheel and the chassis is already very strong in water. But when you remove water, you remove a solvation penalty. So it makes the bond between the wheel and the chassis even stronger. And the interaction is really, really strong. Now, it's very surprising that it seems to be easier to break the chassis than to remove the wheel from the chassis. To the best of our knowledge, it's a first.
Thank you. We have a question in the back.
Yeah, we have an online question from Beck Crew, Crinkling News, Australia. She wants to know, can you tell us what some of the other teams' goals were in the race?
So other teams, more or less similar but not exactly the same. So the German team, for example, they use kind of windmill. Is not the real car shape. The Basel team from Switzerland, actually who won, they did not use the real car shape either. They use kind of a smaller molecule which is commercially available, and so they just try to move the small molecule. That also part of the reason it's easier to manipulate. The French team and our team, we really try to develop the real car-shaped molecule, and the French cars, of course, they won, by the way, the most beautiful car during the competition, but it's difficult to drive, and so they were also learning process to improve. The Austrian and Rice University combined team, in their case, they design also like the real car. However, they could not complete. They should speak for themselves. But nevertheless, they could not complete the whole car. So they entered the competition only with the 2 wheels instead of 4 wheels, half of the car, and on the silver surface, which is flatter. But they drove much farther away and they won. So the 2 teams who won, in a way, did not have the real car structures of a 4 wheel like us. And the Japanese team has a really nice idea. They use kind of develop the molecules. They want to vibrate the molecules. By means of vibration, the molecule will move. But it was also the learning process that for some reason they did not succeed during the race. But my understanding is that they were successful during the training period. So we basically managed to drive the real car and tag as a 4-wheel in nanos, and up to was 38 3 nanometer, and we could not continue because our Ohio by the town was affected in competition in France because we were remotely competing.
Okay, did you want to add anything to that?
Oh, sure. So, as Professor Hla said, there were other cars who had different designs. I mean, in our case, it's the only supramolecular car of the race. And I just wanted to add like an interesting feature of mention a specific feature of the car. It does really behave on the surface like a real car. It has the 4 wheels, sliding or rolling on the surface. But when the wheel gets dislodged, I mean, there are a few, as I said before, it's very difficult to remove a wheel. But there are a few wheels that have been dislocated from the chassis. And when the wheel falls off the car, it does exactly what a wheel of a regular car would do. It would sit flat on the road. So we can see here on a supramolecular perspective, we can have 2 different arrangements. We can have an arrangement where the wheel is sitting on the surface via its portal, so when the car loses the wheel, or it can sit on its equatorial rim when it's on the car, which is exactly what we see in a regular car. Yeah.
Do we have another question in the back?
Yeah. Let's see. We have Tom Whipple from the Times. Can you go a bit more into the rules? How nano does it have to be? That is, a small iron filing could easily be propelled fast and far using a magnet. What are the constraints?
So the question is how fast and what are the constraints? Is that correct?
It's kind of like what are the rules of this contest? What were the parameters that they set for you?
Okay, so the parameters that they set, basically, we have to drive either electrical or electronics energy by using electrical energy or electronics energy, electrons, and that's number 1 rule. Number 2 has to be on gold substrate, and I believe this is the car has to be at least 100 atoms or more. And number 3, we are not allowed to push. It's like, we have to drive, not push with the tip. And it requires to turn, not just to drive. It has to show that you can turn the car to the left and then back to the right. And so that's the points. And the racetrack is 100 nanometer. Is it correct, Eric?
Oh, that's
100
correct.
nanometer, right. So those are the rules. And of course the hours, which is I think 36 hours altogether. Now, how fast is another different question, because so most of the case, in my opinion, this is not about how fast, because when we move the car, we have to first take the image of the car, and then we inject or apply the electric fields, the car moved. In order to check the car actually moved, we have to take the next image frame to compare with the previous image frame. The car moves, we know. So now, how fast in this race is how fast you take the image frame rather than how actually the speed of the car. This is probably less scientific in this case. However, I think it's fine to get the public attention. Scientific point of view, I would say that these nano cars moved in the range of probably about also in nanoseconds frame. They are super fast to the point. but they don't go too far. So if you apply, they move short distance in a very fast, and they stay there and waiting for the next injection of the energy. So we are injecting the energy not, it's not self-driving. So we are providing the energy step by step. Does it?
And to add to this,
please go ahead. Eric.
in our case, since the wheels are really big, the chassis does not interact with the surface. Right, so it really separates the surface from the chassis, and the only point of contact between the car and the surface is via the four wheels. So we expected the car to move really fast, and there is such little interaction between the assembly and the surface.
Any further questions? All right, well, thank you very much. The archived version of this session will soon be posted at bit.ly/ACSLive_DC. This concludes our last press conference for this meeting. Thank you so much for joining us, and we hope to see you again at our next national meeting in New Orleans.
Thank you.
Thank you.